I'm using OrthogonalMatchingPursuit, a specific algorithm for fitting a model. It's like finding the best way to describe something using only a few key ingredients. In this case, the recipe is a linear model, and the ingredients are the features. The model's goal is to accurately predict the target. I'm using scikit-learn's OMP to model a dataset. We have features, think ingredients, and a target, the dish we're making. My goal is to figure out how these features interact to make the target. This describes the features. It's a table. I have 100 observations and 50 different features for each observation. It is like a spreadsheet with 100 rows and 50 columns. This is what I'm trying to predict. For each of the 100 observations, I have a corresponding single target value. It's a single column in a spreadsheet with 100 values. This parameter is super important. I want to keep my model simple. I'm forcing the algorithm to use only 10 of the 50 features to make predictions. I am only allowing a maximum of 10 ingredients in my recipe. This statement is incorrect. OMP is a greedy algorithm. It makes locally optimal choices at each step. It doesn't guarantee that it'll find the best 10 features overall. This is true. The _n_non_zero_cofs parameter tells OMP to select only 10 features. That's how this works. This is false. OMP provides an approximation. It tries its best to get close, but perfectly reconstructing the target isn't guaranteed. This is wrong. OMP is greedy. It might find a good solution quickly, but it does not guarantee to find the absolute best possible solution. I'm focusing on statement C here. This statement is true. The parameter _n_non_zero_cofs equals 10 directly tells the OrthogonalMatchingPursuit (OMP) algorithm to select at most 10 features. It means the model will give non-zero importance to exactly 10 features. Think of it as having a budget of 10 features, and the OMP algorithm uses up the entire budget. This is a core feature of OMP. This statement is incorrect. OMP uses a greedy approach. It doesn't consider all possible combinations of 10 features. Instead, I can describe it as, at each step, OMP selects the feature that best reduces the error from the previous step. That's why it doesn't guarantee finding the globally best 10 features, only the best it can find along the path it's taking. Statement B is false, unfortunately. OMP is an approximation method. Even with 10 features, it's unlikely the model will perfectly predict the target. Think of it like trying to fit a curvy line with just 10 straight line segments. You get close, but not perfect, and the quality of the fit depends on the data. This is also false, similar to statement A. Because OMP is greedy, it makes the best decision it can at each step. But because it never looks ahead, it doesn't guarantee to find the absolute best solution among all possible sets of 10 features. It's like taking the quickest route up a mountain. You might reach the top but not necessarily the highest peak. I'm going to explain why this statement is false. OrthogonalMatchingPursuit, OMP, is a greedy algorithm. Think of it like this. At each step, OMP grabs the feature that seems best at that moment, without considering the bigger picture. It doesn't look ahead to see if there's a better combination of 10 features overall. Therefore, it's not guaranteed to find the absolute best solution. There might be other combinations of 10 features that would give a better result, but OMP might miss them. OMP, or OrthogonalMatchingPursuit, is a clever algorithm used to find a small set of features that are most important for predicting some outcome. It works iteratively. At each step, it picks the feature that's most strongly correlated with what's asterisk left to explain. This is a crucial parameter in OMP. It tells the algorithm to use at most 10 features in its final prediction. In other words, the model will produce a prediction based on only 10 of the available 50 features, ensuring that at most 10 coefficients are non-zero. This statement is true because of the _n_non_zero_cofs equals 10 parameter. The OMP algorithm, under this setting, is instructed to select exactly 10 features, which directly translates into having exactly 10 non-zero coefficients in the model. After OMP finishes running with the data and the _n_non_zero_cofs parameter set, the fitted model represents the result. This model uses only the selected 10 features to make predictions. This describes our data. We have 100 samples, and each sample has 50 features that might be helpful in making a prediction. This is what we're trying to predict. For each of the 100 samples, we have a single target value. The OMP algorithm uses the feature matrix, X, to predict this target vector, Y. We are using a specific type of model called OrthogonalMatchingPursuit, OMP. It's designed to find a sparse representation of the data, meaning it tries to use only a small subset of features to make its predictions. I'm using scikit-learn's OMP, a model-fitting technique that helps me find the most important features in my data. Think of it like trying to build a Lego castle with only a limited number of bricks. OMP helps me strategically choose the best bricks. This is my data. It's a table with 100 rows, observations, and 50 columns, features. Each row represents an example, and each column represents a different aspect of that example. This is what I'm trying to predict, a single value for each of my 100 examples. It could be anything like the price of a house, the success of a marketing campaign, or even a person's health status. This is the crucial parameter. I'm telling OMP to use at most 10 features when building its model. I'm limiting the number of important features I allow it to choose. After running the algorithm, I have a mathematical model that helps to predict the target value based on the 10 selected features. It's like building a Lego castle using only 10 bricks, the best bricks, according to the OMP algorithm. This tells the OrthogonalMatchingPursuit, OMP, algorithm to select at most 10 features when building the model. Think of it like this. I'm giving the OMP algorithm a budget. It can only use 10 features to explain the data. The OrthogonalMatchingPursuit algorithm is a clever method used to find the most important features in a dataset, one by one. It's like a detective searching for clues. It finds the feature most strongly related to the crime, the thing we're trying to predict, then looks for the next most important feature related to the remaining evidence, and so on. It's a greedy algorithm. That means it focuses on the best immediate solution, even if it might not be the absolutely best overall solution in the long run. This is the question that tests my understanding of how the OMP algorithm works given the specific constraints. This is what I'm trying to predict using the selected features. It's a list of 100 values. Each value corresponds to a sample in the dataset. This is a table of data. It contains information about 100 samples, and each sample has 50 features. Think of each row as a different person, and each column as a characteristic like height, weight, age. The OMP algorithm will use this to create a predictive model. After the OMP algorithm runs with the n_non-zero_cofs constraint, I will have a list of at most 10 features that the algorithm identified as the most important for predicting the target variable. These are numbers that tell me how much each selected feature contributes to the prediction. Since I only chose at most 10 features, there will be at most 10 of these coefficients. They're called non-zero, because any feature not chosen will have a coefficient of 0, and those are ignored. This is the type of model I am using to analyze data. Orthogonal means that each feature is considered independently of the others. MatchingPursuit refers to the greedy approach of iteratively adding features that improve the prediction until the budget of 10 features is reached. I'm using the OrthogonalMatchingPursuit, OMP, algorithm, a greedy method for finding a sparse solution in linear regression. It means that at each step, OMP makes the choice that seems best at that moment, without considering the overall best solution. Think of it like building with Lego. You grab the brick that seems to fit best, without thinking too far ahead about the complete structure. OMP works iteratively. I select features one by one. At each step, I choose the feature that best correlates with the part of the target variable that I haven't explained yet, the residual. It's like solving a puzzle piece by piece. Once I've selected a feature, I calculate the coefficient, the importance of that feature, for its contribution to the model. It's like assigning a value or weight to each selected Lego piece based on how well it fits into the puzzle. After calculating the coefficient, I update the residual. The residual is the difference between the actual target variable and what my model predicts so far. I continue selecting features and updating the residual until I meet a specified condition. It's like adjusting the structure continuously to better fit the overall shape of the Lego creation. This is the data I want to predict. It's a vector, a single column of numbers, with 100 values, one for each of the 100 samples I have. Think of it as the ideal Lego structure I'm trying to build. This is my input data. I have 100 samples, and each sample has 50 features, different characteristics that might help me predict the target vector. Think of it as the box of 50 different types of Lego pieces. The parameter n_non_zero_cofs equals 10 tells OMP to select exactly 10 features, or less if the problem is perfectly solved with fewer. Only those 10 will have a non-zero coefficient, the rest will be zero. It means only 10 Lego pieces will be used in my final model. The whole process of using the OMP algorithm to build a model that explains the relationship between the features and the target is called OMP model fitting. It's like building the Lego structure using the chosen OMP method. This parameter is crucial. It sets a limit on the number of features I can use in my model. I will select at most 10 features and set the coefficients of the remaining features to 0. Think of it as having only 10 slots to place my Lego pieces. I'm using the OrthogonalMatchingPursuit algorithm, a method for finding a sparse solution to a linear regression problem. Think of it like trying to explain complex data using only a few key factors. My data has 100 different observations, each described by 50 different characteristics or features. Imagine 100 people and 50 pieces of information about each: height, weight, age, etc. This is what I'm trying to predict. For each of the 100 people, I have a single value, maybe their income. I'm only allowing myself to use a maximum of 10 of the 50 features to build my prediction model. This makes the model simpler, and helps prevent overfitting. It's like trying to understand income based on only 10 factors out of 50. This is a specific type of algorithm that works step by step. At each step, it picks the feature that's most helpful in explaining the data, leaving less to explain in the next step. It's a little like building with Lego. You add the biggest bricks first. The algorithm works iteratively. It doesn't look at all the features at once. Instead, it makes choices one feature at a time, based on what helps best at each step. It is like searching a huge maze one step at a time. I'm forcing the model to be simple, using only 10 features. This constraint leads to a solution with at most 10 non-zero coefficients in the final equation that predicts income. This is my trained model. After feeding my data into the OMP algorithm, I get a model that predicts income based on my chosen features. My final model will use no more than 10 of the 50 features. The equation produced by the model will have exactly 10 coefficients that are not zero. Each coefficient shows the importance of a selected feature in predicting the income. This is a multiple-choice question to test your understanding of OMP and its behavior under a sparsity constraint. This is false because OMP is a greedy algorithm. It chooses the best feature at each step, not the overall best 10. Think of it like choosing the best ice cream flavor one at a time, not picking the 10 best all at once. This is false. OMP provides an approximation, not a perfect reconstruction, especially with a limit on the number of features. It's like trying to draw a perfect circle with only 10 straight lines. You'll get close, but not exactly perfect. This is true. The n_non_zero_cofs parameter directly controls this. This is false. Because OMP is greedy, it doesn't explore all possibilities. It might miss a better combination of 10 features. It's like finding the highest hill in a mountain range by only ever walking uphill. You might find a high hill, but not necessarily the highest one.